Where does the solar system actually end? Astronomers can point to 8 planets, name their orbits, calculate their masses, and predict their positions centuries into the future. And yet, ask a simple question: where does the solar system stop? And the answer falls apart. There is no wall out there, no sign, no clean boundary where the sun's domain ends and something else begins. For decades, researchers gave a confident answer anyway. The edge was wherever the planets stopped. Neptune marked the border. Beyond that, emptiness. That answer felt complete. It fit on a diagram. It fit in a textbook. And it was wrong, because once probes actually left the planetary region, they kept finding things. Disks of icy bodies, pressure waves from the sun colliding with the galaxy, hints of clouds and bubbles, and structures that stretch for trillions of miles. The boundary kept retreating, again and again, every time we thought we had finally reached it. This is the story of that retreat, a story about how far our solar system actually extends, what surrounds it, and why the answer might still be incomplete. The obvious explanation is the one most people grew up with: 8 planets, orbiting in a flat disk around the sun. Mercury closest, Neptune farthest, and past Neptune, nothing. Just the dark. For a moment, that seems reasonable. The orbits really do form a disk. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, all moving within a few degrees of the same flat plane. A plane astronomers call the ecliptic. It looks tidy. It looks finished, but there is a problem. That picture only describes a thin slice of space, a flat pancake, and space is not flat. The moment you ask what lies above that disk, or below it, the textbook diagram has nothing to say. So we have to ask where that disk came from in the first place. Because the answer to that question is also the first clue to everything that surrounds it. Roughly 4.6 billion years ago, before Earth existed, before the sun had even ignited, there was only a cloud, a vast, slow-moving collection of gas and dust drifting through the galaxy. Something disturbed it. Maybe a nearby supernova. Maybe the gravitational nudge of a passing star. The cloud began to collapse under its own weight. As it collapsed, it spun faster. And as it spun, it flattened, the same way a ball of pizza dough spreads into a flat circle when you spin it fast enough. Physics left no other option. The result was a rotating disk of material surrounding the newborn sun, and within that disk, the planets formed, gathering dust and gas over millions of years. That's why the planets share roughly the same orbital plane today. Not because the solar system was designed that way, but because every planet inherited the shape of the cloud that built it. Not everything fell perfectly into line. Mercury's orbit tilts about 7 degrees from the ecliptic. Pluto's tilts nearly 17. Some comets arrive at almost right angles to the planets. Like needles through a record, leftovers from a far more chaotic early solar system. But the 8 major planets stayed close to the original plane. A flat disk inherited from a cloud that collapsed billions of years ago. And that flat disk is where the textbook stops. Which is exactly where the real picture begins to diverge from it. Here is something most diagrams never show. The plane of our solar system, that flat disk containing all 8 planets, is tilted about 60 degrees relative to the plane of the Milky Way galaxy itself. Picture the galaxy as it is usually drawn. A flattened spiral of stars, with arms curling outward from a dense central bulge. Our solar system sits inside that spiral, roughly 26,000 light-years from the galactic center. But we are not lined up with it. We are tipped on our side like a coin balanced at an angle on a table. That single fact changes the meaning of above and below. When people ask what lies above or below the solar system, they are not asking about some fixed direction in space. They are asking about a direction relative to our tilted little disk. A disk that itself is angled against the much larger structure we're embedded in. And we are not sitting still inside that structure. The sun is moving. It travels around the center of the Milky Way at roughly 515,000 miles per hour and 1 full circuit, 1 galactic year. takes somewhere between 225 and 250 million years. Because of that 60-degree tilt, our path through the galaxy isn't a flat line. We rise and fall relative to the galactic plane as we orbit, like a horse rising and dropping on a carousel. So, above the solar system and below the solar system are not abstract directions. They are directions we are actively moving through, on a journey measured in hundreds of millions of years. On Earth, up and down feel absolute. Gravity defines them before we're old enough to understand the words. The sky is up. The ground is down. There is no ambiguity. In space, that certainty disappears. There is no floor. No ceiling. No universal up or down. Only relative positions, and an astronaut floating in orbit could be upside down compared to a colleague a few feet away, and neither of them would be wrong. There's no correct orientation when nothing is pulling you toward a particular side. So when astronomers talk about what's above or below the solar system, they're making a choice. They use the ecliptic, the plane of the planets, as a reference line. It's a human convention, useful for mapping, but arbitrary in any cosmic sense. And once you adopt that reference frame and start hacking what actually exists, above and below it, the flat, finished-looking diagram of the solar system starts to look less like a picture of everything, and more like a picture of almost nothing. The first thing you find isn't above or below at all. It's everywhere, a thin haze of debris stretching outward from each planet's orbit, forming what's sometimes called the dust disk, made of collisions between asteroids and crumbling comets, faintly visible from Earth as a glow in the night sky. But that disk is just the beginning, and the next structure is one we have never directly seen, out past Neptune, at roughly 30 astronomical units from the Sun. The orderly orbits of planets give way to something else, a vast, theoretical shell of icy bodies that astronomers call the Oort Cloud. Unlike the planets, the Oort Cloud isn't confined to the flat disk. It surrounds the entire solar system in 3 dimensions, above, below, in front, behind, like a shell wrapped around an egg. Estimates put its inner edge at roughly 2,000 astronomical units from the Sun, and its outer edge as far as 100,000 astronomical units, nearly a quarter of the distance to Proxima Centauri, the nearest star beyond our own. We've never imaged a single object in the Oort Cloud directly. The bodies there are thought to be small, dark, and almost unimaginably far away, too faint for any telescope we currently have. So why are astronomers confident it exists at all? The evidence comes from comets, specifically long-period comets, the ones that take thousands or even millions of years to complete a single orbit around the Sun. And these comets don't arrive from the flat plane where the planets orbit. They come from every direction. Above, below, angles no planet has ever traveled. That spherical pattern of arrivals is a signature. Something out there, distributed in a sphere rather than a disk, is occasionally getting nudged inward and falling toward the Sun. The Oort Cloud is the explanation that fits, an invisible shell of ancient debris, leftover material from the same cloud that built the planets, flung outward early in the solar system's history by the gravity of Jupiter and Saturn. Some of that material escaped the solar system entirely, lost to interstellar space forever. The rest settled into enormous, slow orbits, and 4.5 billion years later, it's still out there, completely surrounding us, completely invisible, and only detectable because every so often, a piece of it falls. If the Oort Cloud were the actual edge of the solar system, this would already be a strange enough place to live. Wrapped in an invisible shell of comets, stretching nearly a light year in every direction. But it isn't the edge. It's barely past the beginning. Because long before you'd ever reach the Oort Cloud, you'd run into something that itself is actively building every second of every day. The Sun isn't just a source of light. It's constantly shedding material. A stream of charged particles called the solar wind, made mostly of protons and electrons, blasted outward in every direction at hundreds of miles per second. As that wind expands outward, it eventually runs into something pushing back, the thin gas and dust that fills the space between stars, known as the interstellar medium. The collision between the sun's outward wind and that interstellar material inflates a kind of bubble around the entire solar system, a bubble called the heliosphere. For a while, it might seem reasonable to picture this bubble as a perfect sphere, evenly inflated in all directions. That would make sense if the sun were sitting still, but it isn't. The sun is moving through the galaxy, and that motion changes everything about the bubble's shape. Picture a boat moving through water. A wave piles up at the bow. A wake trails out behind. The heliosphere behaves the same way. Compressed on the side facing our direction of travel, stretched out into something closer to a long teardrop on the trailing side. The boundary where the solar wind finally runs out of momentum and starts mixing with interstellar material is called the Heliopause. It's the edge of the sun's direct influence, the place where inside our bubble ends and the rest of the galaxy begins. And we've actually been there. Voyager 1 crossed the Heliopause in 2012. Voyager 2 followed in 2018. Both spacecraft are now traveling through interstellar space, the first human-made objects to do so. And yet, even having crossed that boundary, they are still, technically, within the outer reaches of the Oort Cloud. Two boundaries, two different definitions of the edge. And neither one is the final word. Because once you're past the Heliopause, past the sun's direct influence, you might expect to finally be in true emptiness, the void between stars, with nothing left to study. That expectation doesn't survive contact with the data either. The region of space the sun is currently moving through has a name, the local interstellar cloud. It's a patch of slightly denser gas and dust within the broader interstellar medium. Not dense by any everyday standard, still emptier than the best vacuum chambers built on Earth, but denser than the space around it. Enough to matter. Enough to be the very thing the heliosphere is pushing against, shaping its teardrop form. And this cloud isn't flat either. It extends above and below the ecliptic plane, surrounding the solar system in 3 dimensions. Just like the Oort Cloud, a different kind of structure, at a different scale, but following the same pattern. Nothing out here respects the flat disk we started with. The sun has been moving through regions like this for billions of years, and will continue doing so for billions more, sometimes denser, sometimes sparser, an endless journey through a galaxy that is anything but uniform. At this point, a pattern starts to emerge. Every time researchers thought they'd found the outer wall, the planets, then the Oort Cloud, then the Heliopause, something larger turned out to surround that boundary too. So it's worth asking, how far does this go? Is there a structure that contains all of it? And if so, what created it? The answer to that question takes us somewhere unexpected. Not towards something the solar system built, but towards something built around the solar system long before it arrived. Zoom out far enough, and the solar system isn't just sitting in ordinary interstellar space. It's sitting inside a cavity, a region roughly 1,000 light-years across, where the density of surrounding matter drops sharply. Astronomers call it the local bubble. It isn't empty, exactly, but compared to the gas and dust filling the rest of the galactic neighborhood, it's startlingly hollow, a pocket carved out of the cosmic fog. What carved it? Supernovae. Researchers estimate that at least 15 massive stars exploded in this region over the past 14 million years. Each explosion blasted gas and dust outward with tremendous force, and over time, those repeated blasts hollowed out the cavity the solar system now occupies. Here's where it gets stranger. The solar system wasn't always inside this bubble. About 5 million years ago, our path through the galaxy carried us into it. We crossed through the bubble's outer wall, a denser shell of gas and dust, piled up at the edge, like snow pushed aside by a plow, and we have physical evidence of that crossing, preserved on Earth. deep-sea sediments contain elevated levels of iron-60, a radioactive isotope that can only form inside a supernova. The timing of those deposits lines up with when the solar system would have been passing through the local bubble's shell. In other words, the ground beneath our feet, the ocean floor, contains a chemical record of an event that happened millions of years before humans existed, written by stars that died long before our planet had any inhabitants capable of reading it. We are floating inside a structure that didn't exist when life on Earth began, shaped by explosions, some from stars whose names we will never know. In a region where new stars are now forming again, triggered by the same compression that built the walls around us. It would be comforting to think that the local bubble is finally the big picture, a single cavity, with the solar system somewhere near its center, and nothing more to explain. For a moment, that might even seem like enough. 1,000 light-year bubble is already almost incomprehensibly large. But the local bubble isn't a boundary to the universe. It's a feature embedded in something far larger, the Milky Way itself. And the Milky Way has its own above and below to consider. The galaxy isn't just the flat spiral most people picture, the one with sweeping arms and a bright central bulge. Surrounding that disk, extending far above and below the galactic plane, is a roughly spherical region called the Galactic Halo. The halo contains some of the oldest stars in the galaxy. Stars that formed before the spiral arms existed, before the disk had even fully taken shape, drifting in orbits that carry them far above and below the plane where younger stars like the Sun reside. It also contains globular clusters, dense balls of ancient stars, and it's thought to hold a significant fraction of the galaxy's dark matter, the unseen mass that outweighs ordinary matter and holds galaxies together gravitationally, even though it has never been directly detected. So now there are two separate definitions of above and below stacked on top of each other, relative to the ecliptic. Above means out of the plane of the planets, into the realm of the Oort Cloud, the Heliosphere, the local interstellar cloud. Relative to the galactic plane, above means out of the disk of the Milky Way entirely, into the halo, amongst stars older than the Sun itself. Embedded in a sea of matter we can't see and can only infer. Neither reference frame is more correct than the other. They're both arbitrary, useful conventions for describing direction in a universe that has no built-in floor. And that, more than any such a single structure, might be the actual discovery here. Start adding it up. The flat planet is real, but it's just a thin slice through something far bigger. Surrounding that disk, a spherical shell of ancient comets, nearly a light year across, that we've never directly seen. Surrounding that, a bubble of solar wind, shaped like a teardrop by our motion through the galaxy. Surrounding that, a slightly denser patch of interstellar gas that the Sun happens to be passing through right now. Surrounding all of it, 1,000 light-year cavity carved out by supernovae that exploded before humans existed, which we only entered 5 million years ago. And surrounding the entire galaxy itself, a halo of ancient stars and invisible matter stretching far above and below everything we've described so far. Each layer was, at some point, treated as the edge. Each one turned out to be a thin boundary inside something larger. So, where does the solar system actually end? The honest answer might be that the question itself assumes something that isn't true. It assumes there's a single edge, a single shell, a final boundary, where the solar system stops and everything else begins. But what the evidence actually shows is layers, nested structures at wildly different scales, each shaped by different forces, each with its own boundary, and none of them final. The solar system isn't a sealed object sitting in empty space. It's a region of space, embedded in another region, embedded in another, all the way out to the scale of the galaxy itself. And the galaxy is embedded in something larger still. We are, right now, inside a 1,000 light-year cavity that didn't exist when the dinosaurs walked the Earth. moving through a patch of interstellar gas that the sun will eventually leave behind, surrounded by a shell of ancient comets inside a bubble of solar wind shaped by our motion through the galaxy. Tilts at 60 degrees against the plane of the Milky Way, rising and falling through that plane on a 225 million year orbit. None of us will live to see complete. None of that is visible from a backyard telescope. None of it shows up on the diagrams in a classroom, and yet all of it is, right now, exactly where we are. The next time someone asks where the solar system ends, the honest answer isn't a number. It's a question right back. Which boundary do you mean? And are you sure it's the last one?